So we're very happy to have Raghu Mahajan from ICTS with his last lecture on the black hole information problem.
Okay, thanks Prateek. So today we will finally get to calculating these entanglement wedges which have disconnected parts in a simple example of two-dimensional dilaton gravity. Because the matter fields that we'll couple to our gravity will be conformal, so the first part of this lecture will be just about entanglement entropy formulas in 2D CFT. Okay. So some part of this has probably already been covered in maybe some lecture, but we will just review some basic facts that we will need. So we consider a CFT2 on just spatial line, the infinite spatial line in the ground state. Okay. So that's the first case. And this is the simplest case to study. So here I have drawn the setup. So we have some infinite spatial line and time. We will get to the light cone coordinates and this part of the figure later, but for now, let's say we have some interval AB. Then it is known that SAB is C over 3 log of L over epsilon, where L is just the length of AB, so we are just in Minkowski space, and epsilon is UV cutoff. And the entanglement has to be divergent because of the short distance nature of any quantum field theory. Okay, so let's just write this as C over 6 log of L square over epsilon square. Okay, so this is one fact. But now I also want to write a formula for the entanglement entropy of this PQ line segment. So P and Q don't lie on the same spatial line, but they're kind of tilted like this. But PQ is still space-like. The line segment PQ is still space-like. So we can draw this diamond, right? I shoot light rays from P and from Q, and we get this diamond. So there's an entropy that is naturally associated to this diamond. And since everything here is Lorentz invariant, the entropy should just depend on the invariant length squared of PQ. So in light cone coordinates, we can write that as x plus of Q minus x plus of P times x minus of P minus x minus of Q divided by epsilon square, right? So this difference is like this gap here, that's the difference in the x plus coordinates, and this difference here is the difference in the x minus coordinates. Yes, that's yes. Yes. So it's the entropy of AB when you trace out the complement, the line segment AB, yeah. So this is what this was supposed to mean. Okay, so this is this Lorentz invariant fact. So I just wanted to display this formula, that was the main point. And note that the coefficient here is like 6 instead of the 3, okay. So next, what we will need is let's say now you're not in flat space, but there's a CFT2 on a conformally flat space. So there's a conformal factor omega, which could be a function of t and x, and you still have minus dt square plus dx square. Okay. So when we have this space, there will be so the coordinates of the endpoints will still be labeled by t and x, but there will be an extra contribution to the EE, which is equal to negative C over 6 log of omega at the endpoints. So you sum over all the endpoints and you have to put in a log omega factor. Now, how do you see this? One way to see this is that this epsilon is supposed to be a proper cutoff. So the proper cutoff clearly depends on omega if you fix the coordinate cutoff. So that's where this contribution comes from. Another way to see the same thing is that in the replica trick, these entanglement entropies or any entropies are calculated by 2-point functions of twist operators. And if you calculate the 2-point function on this space, the 2-point function depends on omega, like omega to the delta. So there is some omega dependence which will be important for us. Okay, so now what we will do is we will use this formula to do first a practical calculation, okay? So a practical calculation will be, now it's a CFT2 on spatial, it's still R, but in finite temperature state. Okay, so we still have infinite Minkowski space, but now the gas, the CFT is hot. Okay, so I'm just going to change coordinates and I'm going to call this y plus and y minus, okay. So it's important to note that there is some hot gas here. It's not just in the vacuum, so, okay. And now we again want, let's say, the entanglement entropy of an interval AB. So what is S of AB? So it will be some function of, let's say, B minus A and beta, right? So B is just the coordinate of B and A. So this is 0, A, this is 0, B. In the time and space coordinates. Okay, so we want to somehow use this result to derive this. So here is the idea. So we do, first it's maybe helpful to draw it as a Penrose diagram. So the Penrose diagram looks like this of this space, but it's hot here. So we somehow want to introduce a second copy of this hot space such that this half is purifying this half, right? So you have a thermal state here, you can introduce a second copy such that the total state is a pure state. And we already know from the first lecture what this will be, right? So there will be some larger Minkowski space such that our initial space is embedded as a Rindler patch in the bigger space. So that is the trick. Okay, so how do we do this? Define a new coordinate, x plus, and that is equal to e to the y plus. So notice that this belongs to 0 to infinity, and x minus is defined as negative e to the negative y minus, and this belongs to minus infinity to 0. Okay. So we have these half-sided half intervals. So let me draw a different figure now. So what we have done is that in the x plus x minus plane, we have embedded all of the original space as just the right Rindler patch, right? X plus is positive and x minus is negative here. Okay, so but what's the metric? The metric ds square in the original case was minus dy plus dy minus. Using that coordinate transformation there, you can write this as negative dx plus dx minus over negative x plus x minus, and this is right now is just valid on this R plus region. Okay. because this while factor is singular at the horizon, because it goes to 0 there. Okay, so now we have a form of the metric in the x plus coordinate with a omega which is equal to, where omega to the -2, what convention did I use? Yeah, so omega to the -2 is negative x plus x minus to the -1. So omega is negative x plus x minus to the 1/2. Okay, and our interval, that AB sits somewhere here, right? It's in here. Now we use that formula, because now we say, consider a global pure state in this metric. Okay, so the state in the x plus x minus state is pure on this whole slice, and then we can now use start using those formulas. So basically, S of AB will be actually, let me make a table. So we have this point A and the point B. We have the t comma y coordinate being 0 comma A, 0 comma B. So the y plus and y minus coordinate, just add and subtract them. It's A minus A, B minus B. So x plus x minus coordinates are e to the A minus e to the A, and e to the B minus e to the B, right? We can check that these two had to add up to 0 because this line is x plus plus x minus equal to 0. Okay, so now we plug it in. So we have c over 6 log of, it was the difference in x plus. So e to the B minus e to the A plus c over 6 log of the same thing minus c over 6 log of this omega factor. So omega is e to the A minus c over 6 log of e to the B. Okay, let me write here where these terms came from. So this came from log of delta x plus, this came from log of delta x minus c over 6 log of omega at A minus c over 6 log of omega at B. Okay, are there any questions about this, how we wrote this expression? It's just using the results on the previous board. Okay, so yes. Yes. Right. So the idea is that the original Minkowski space we started with is while equivalent to only a subregion of this space. So one should not try to extend it beyond that. Then you have to do the usual trick of complexifying some coordinates and going to some Euclidean theory, like the relation between Kruskal and Schwarzschild. The one you start with is only valid in the right right wedge. So it's like that. And it's important that the global state in X plus is bigger than your original space, because that's how you're purifying the state, right? Okay, so what does this give us? We just simplify and we get C over 3. Just trust me, this is a simple calculation. Log of 2 times sinh of B minus A over 2. These two terms are the same and you just divide that, you get this sinh. So here we secretly set the temperature to 2 pi, but the generalization would be C over 3 log of beta over pi sinh of pi over beta B minus A. And in the limit that B minus A is much, much bigger than beta, we just get C over 3 times pi over beta times B minus A which is like C times B minus A times the temperature times some constant, right? And this is the physical answer we should have expected. We just have a thermal state on an infinite line. And since it's conformal, the answer has to be extensive. So it has to be proportional to B minus A. And to make it dimensionless, it has to be multiplied by the temperature. And the C comes because the C is the measure of the number of degrees of freedom. So these three factors are kind of obvious. And then this pi over 3 is the thing that you calculate from this. But when B minus A is comparable to beta, this formula you can still use, which is not linear in B minus A. Okay, so this is a way of deriving the finite temperature entanglement entropy of an interval on R by this conformal transformation method. Yeah. Oh yeah, I dropped the epsilons in the thing, but they should be here, yeah. That part is universal. Okay, any more questions about this? Okay, no, so good. So this was just some review. These are the formulas we will use later. Yeah. So this is with beta equal to 2 pi. It's just because I did, that transformation with coefficients 1. So it's just dimensional analysis to restore the things back. And the epsilon will go here to make it dimensionless. Okay, so now let's come to the problem that we ended up with last time, which was these two SYK models coupled to two wires. But since I still haven't introduced JT gravity, and I don't think anyone has even talked about that, right, in the school. So yeah, so we need to quickly review what that is. So as I was mentioned, SYK should be thought of as a theory of n fermions that live in time. So this is, you can think of it as a one-dimensional world line of these particles. And the conjecture is that this is dual to, in some kind of ADS2 CFT1 correspondence to a two-dimensional ADS space. So this is ADS2 space with a time coordinate and a z coordinate. And so this is the thing I just want to explain briefly. The action of this gravity theory is somewhat simple. So the action that is supposed to go here is minus 16 pi g I Euclidean equals phi naught chi plus integral d to x root g phi r plus 2 plus 2 integral dx root gamma phi k minus 1. So this is the Euclidean action if this 2D theory was placed on a manifold with Euler character chi. So this is the topological term. And then there is a dynamical dilaton and the dynamical metric. And this is some boundary terms. You need the k term because of Gibbons-Hawking and to make the Dirichlet problem well defined. And this minus 1 is there as a holographic counter term to make the on-shell actions finite and so on. Okay, so this is the action. And you can write the equations of motion. So we would be interested in finding solutions with a disk or cigar topology, which is the same. Okay, so when you vary the action with respect to phi and set it to 0, it's easy to see that the equation of motion you get is r plus 2 equal to 0. So this is nothing but saying that it's a constant negative curvature space. And since we want to find a solution with the disk topology, we just write down the metric of hyperbolic 2 space. The metric is d rho square plus sinh rho square d theta square. So rho is the radial coordinate and theta is some angular coordinate. Okay. And this cigar, of course, is supposed to be the Euclidean section of some eternal black hole. But we are not done yet, because we have not yet satisfied the equation of motion for the metric. Now, solving this is a little bit tricky, because the metric dependence is here and here, but you need to know the variation of the Ricci scalar with respect to the metric, and it has some total derivative terms that are usually ignored, because usually you don't have this phi multiplied here. So when you vary the Ricci scalar, you will get, so let me actually write the expression because it's useful. So the variation of root g you have probably all seen, but the variation of the Ricci scalar with respect to the inverse metric has the usual term minus, there is a covariant derivative of the variation, second, and plus del square of delta GAB times GAB. Okay, so when you do the variation, you have to make sure that you take these derivatives and act them on phi. The upshot is that you get the equation grad square phi GAB. This is a term that comes from here, minus grad A, grad B phi, that comes from integrating this by parts, and then this minus phi GAB equal to 0. Okay, so this is the equation of motion. You vary the metric and you got this equation of motion. And you can check that if you plug this metric into here, one possible solution is just phi equals A times cosh rho. So we had a sinh here, there's a cosh here. But, I was too quick. I have not told you yet what the boundary conditions are. So, this A is some arbitrary constant right now, so we need to fix some boundary conditions. The idea is that, because of this sinh rho, this circle is getting very big on the boundary. So we have to introduce some cutoff surface, like we always do in ADS. So this is some cutoff surface. And the boundary conditions are that GTT on the boundary has to be in Lorentzian. Okay, here we can put something. It's minus 1 over epsilon square. So you should think of epsilon as a small parameter, which you need in order to define anything in ADS. And then phi on the boundary should also be big, and it should be 1 over epsilon times a number phi r. Phi r has dimensions of length. Okay. So this is one parameter in the theory which enters. So these are, by definition, these have to hold. So what this will do is, for the metric, it will not do much. It will just tell you where in rho you should put the cutoff. But then you can solve for A in terms of phi r. Okay, so that is what it will do. I will just tell you the answer. So maybe I can just write here that capital A will work out to be 2 pi phi r over beta, where the total length of this circle is beta over epsilon. I think I went over this a little bit quickly, so people should ask questions if the boundary conditions or the solution is not clear. Sorry? Oh, the box of phi r means the dimension of phi r. So, usually people denote it by this box. So this is a dimensionful parameter, and you have this beta here. So in various combinations, the phi r over beta is a dimensionless parameter that controls a lot of things in these theories. Okay, so there's one more thing which I should tell you, which is, okay, so this is supposed to be some Euclidean black hole, so it has to have some entropy. So what is the entropy? Like normally we say the entropy is the area over 4g Newton, area of the transverse space. But here you just have a 2D black hole. There is nothing transverse. Transverse is just a point. But the thing is that phi is sitting here. So what it turns out is that phi plays the role of the area of the horizon. So if you think of a 3D theory of gravity and imagine that you have a 2D space times a circle, this phi at each point on the 2D space is like measuring the length of that extra circle. Okay, so the entropy of the black hole is given by 1 over 4g times phi naught, that comes from here, plus 2 pi phi r times the temperature. Okay, phi r was dimensions of length, so this is dimensionless. So the main punchline is that these black holes described by this theory have a entropy which is independent of temperature, and then the first deviation is linear in temperature. And yeah.
The last term in the equation of motion of phi should be phi times GAB.
Here?
Yeah.
That's what I wrote, right?
No, RAB.
RAB. Oh yeah. Maybe I use some other equation of motion to simplify. Yeah, let's just, we can check it, but maybe you're right. But let me not try to correct it. But yeah, maybe, yeah. You're right. I mean, when you vary, there should be some RAB, but then there is this root G also here. So I don't want to do it on the fly. Maybe I made an error. So, but the solution is definitely correct. Okay, are there any questions? Oh yeah, sorry, good. So, thanks. So RAB is proportional to GAB with the coefficient R. So you can use this. And I think this is true for any 2D metric, not just for ADS2. So for any 2D metric, this is a correct formula. And R is -2, so I guess I have used that to substitute this. Yeah, thanks. Thanks, Onkar. Yes. That's this is dimensionless, so essentially you can absorb it into phi, right? If I divide it here, this really doesn't need to be written. Like you can absorb it 1 over g into phi naught and phi. It's not important. Okay, so, but since we will be doing calculations in Lorentzian signature, now I have to tell you what the Lorentzian continuation of this solution is. I'll just write it. Maybe, yeah, erase this part. Yeah, phi naught is another parameter of the theory, yeah. And it's very important, and it's important that it's very big, because the different genus surfaces will get weighted by this. So this is like, if you think of these 2D surfaces as string world sheets, this is setting the string coupling constant. Yes, it's positive. Yeah, it has to be positive. Roughly speaking, it is capturing again the fact that phi is the length of the transverse dimension, and in ADS3 spaces, you would expect the far away region to have bigger length than something in the center. Yeah, but see here, like as you go outwards, it is increasing, right? And it is reaching the phi r size at infinity. So, right, I have always assumed phi r to be positive. I think it would be a bit strange from this formula's point of view, because typically these, where this comes from is this should be thought of as the entropy of an extremal black hole in higher dimensions. And this is like a correction from the near extremal thing, and this thing is always positive as far as I know. Sorry? That is fine, because we are always dealing with saddle points. So the sign of, yeah, let me not discuss the negative. I think it's not, I may be wrong, but I have never seen any application of it. So, okay, so we were going to continue this to Lorentzian signature. So we first make a change of coordinates, which is d rho over sinh rho. You define a coordinate which is y by this, and you can integrate this to sinh rho equals -1 over sinh y. And it's good to remember that rho belongs to 0 infinity, y will belong to -infinity to 0. Okay, so the metric in these variables becomes sinh y to the -2 dy square plus d theta square. And now if you remember the diagrams I was drawing in the first lecture, this theta is the thing that is supposed to continue to outside time, like the Schwarzschild type time. So this is where we Wick rotate. So t and theta are supposed to form one complex number, right? So we are supposed to think of the number t plus I theta. So we could either be on the purely on the theta slice or purely on the t slice, and you get this metric. And the picture one should have is that ADS2 is represented like this, and these y and t coordinates cover this region. Okay, and the y goes like this and t goes like this. I have chosen y to go like that, it will become clear later, so that's why y is negative. It's 0 here at the boundary, where this warp factor is very big, and it goes to 0 at the horizon. Horizon is at y equals minus infinity. Which is rho equal to 0, which was here, the bifurcation point. Okay, so that's the Lorentzian geometry, which one would say is the dual description of this SYK model to some approximation in the finite temperature state. Yeah. Let me understand. So are you saying, so like in flat space, even though this ADM mass is evaluated at some region and then you take the limit to infinity, it still has a positive theorem, right? There is still a positivity theorem. Only at infinity. Yeah. Yes. Yeah. You mean because in this description, epsilon could be taken to 0, but you're saying when I glue in the flat space, then epsilon is not 0. Well, so yeah, so here we were just doing regular ADS-CFT, and epsilon is always the smallest parameter in the game. So there is no problem. But your question is probably valid once you put in this flat space and then epsilon would be small and finite. Then I don't know, yeah. As I will try to say, like this other kind of holography that I'm now about to introduce is not fully understood. I don't even think it's at least the current understanding is not rigorous. So the setup we had started with last time is we have this two SYK systems that are coupled to these wires that are these heat reservoirs. This thing together is in equilibrium of some coupled Hamiltonian at beta, and this whole thing is the thermophile double purification of this side. Okay, so then the time development of these looks like two half spaces. So we have this half space. If I draw it in time, this will have some SYK degrees of freedom here, and then a second sort of half space here, which has these degrees of freedom living here. Okay, and now the guess or the ansatz or whatever we want to call it that is true to some approximation, but maybe it has a lot of subtleties, is the fact that this purely field theory set up here has a alternative description as the same black hole that I was drawing there. So I'm going to draw it first like this. coupled to these flat space things. So what are these? So basically you take these two SYK, which are in a thermophile double, and replace them by some kind of this geometry that we were discussing there. So this is the ADS2 geometry, and these are the flat space reservoirs. This one and this one here. So, but we are supposed to imagine the following, right? So imagine that you didn't just have that JT gravity, because in order to discuss Hawking process, we always need to have some matter fields. So we have JT gravity plus, let's say, some CFT2, right, to which it's coupled. Now, the physics of ADS black holes, which don't evaporate, is that there's a black hole which is in equilibrium with hot radiation, which is made up of this stuff. And because the ADS is like a box, this radiation cannot escape to infinity. It kind of bounces back and forth, and the black hole comes to equilibrium with this CFT2 at a finite temperature. But it's there, it's like this CFT2 is floating around. Now what you do is you imagine that there is some observer who is very far away, near the boundary of ADS, but not exactly at infinity, like they can't exactly where that's not a point. And they kind of extract out the radiation into some kind of other auxiliary quantum system that they have. So that is supposed to be represented by this. So what you do is, instead of having these CFT fields come in and bounce back at the ADS boundary, instead of putting reflecting boundary conditions, you just let them propagate out. So you kind of change the boundary conditions of the CFT2 at the boundaries. And in fact, we even wrote a paper where this boundary can be partially transmitting and partially reflecting. So you can do all those games. Yeah. If it's fully reflecting, the ADS2 system with the CFT2 is just a complete system in itself, and that's what we were discussing there. But with this coupling, things are a little bit less rigorous and less well understood. So, but still, it seems to give reasonable results for many quantities, so we will just proceed with this. Yeah. 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 Yes, that is true. I agree. So, in fact, I should have cited this much earlier. There is this work by Fiola, Preskill, Strominger, and Sandip, who basically use these CFT2 formulas that I was writing down to define some radiation region and calculate the entropies of the radiation region in the CGHS model. So, and recently there was some paper by Strominger, Hartmann, and Shagulian, maybe one or two other authors, in which they redid this calculation, including the effects of islands. Now again, in all of those setups, this complaint of that Suvrat and others have made about the bath and so on is valid, and I don't have anything new to say about it. Yeah, but then you can't, so in terms of subalgebras, what this allows you to do is to have this tensor factorization between this SYK and this wire, right? Because we kind of have this picture. In order to be able to define a radiation subsystem and a black hole subsystem. So that's what I buy by making gravity sort of non-dynamical in some region. Now, there could be objections that this can't be done and it's impossible, and okay, fine. Sorry? No, I mean this setup here. The gravity coupled to a non-dynamical region. Oh, this is okay. This is fine. Right, but what I'm saying is this is a reasonable get, but can you poke holes in this? Is this rigorous at the same level as ADS-CFT is rigorous? And you'll ask those kinds of questions like epsilon and so on, like where do you glue it, positivity, things like that. Yeah, I guess one thought I had while I was thinking about this, preparing the lecture, if this was some string theory setup, you could have the dilaton go to negative infinity in some region. So then the string coupling, which is e to the phi, would be driven to 0 in some region and not to 0 in some other region. So you can imagine like a dilaton background in which the dilaton is non-zero for some values and then goes to minus infinity at some point. So drives the string coupling to 0. So that's the kind of thing we can imagine. And clearly at the domain wall where the dilaton is doing something sharp, there would be some energy, right? Because the dilaton has some gradient. Yeah.
All the worries of finite cutoff and so on, if you just take the dot literally to be SYK,
Yeah.
and then just say we work at low energy.
No, of course. See, again, as I was saying, there was this paper by Abhishek and Manas and a student, Madhumita, I don't know if she's a student, but they calculated in the quantum system a page curve, right? So there is no doubt that this system, if you think this was at finite temperature and this was a 0 temperature bar, that energy would leak out and the entropy of this region would display a page curve. And there would also be some hydrodynamic entropy, some coarse grain entropy that keeps increasing in time. So there is just no doubt about the validity of the page curve in this setup. The question is like, what relevance it has, if any, to the black hole page curve paradoxes and so on, right? Like that's, and I'm just saying that if you just forget about some kind of information localization subtleties, it's okay to define the radiation region as the region R bigger than 100 M and the black hole region to be R less than 100 M. So if you go with that, then it's okay.
Just to say, I completely agree with the first part of what Raghu said. There's no doubt that in this system you'll see a page curve. There's no question about that. The question is, can you see a page curve? Also in the dual also you will see a page curve. In higher dimensional models, in fact, the transparent boundary conditions and so on make the graviton massive, and then these arguments just don't work. The Hilbert space factorizes in the bulk also. In fact, this 2D case is the one that I think is not so well understood from the bulk perspective, which is why I was asking this. But it's clear that these calculations, I think, are correct. No, the worry in the bulk, there's no worry from the boundary perspective. As Raghu said, there's no doubt you'll see a page curve. The question is, have you modified the bulk theory in some way so that it's not a standard theory of gravity, which is what happens in higher dimensions. In higher dimensions, when you add the transparent boundary conditions, you get a mass for the graviton. In JT, there's no graviton, so you can't talk of a graviton mass. I suspect what is happening is that it's the positivity of energy that's lost in the bulk for the JT gravity theory, but I don't know.
Yeah, in the end, I will present a scenario which no one has done any calculations, but it's reasonable that you can get a page curve in gravity without these baths. So let's just get to that in the end. But I think where the objections of Suvrat and all don't apply, but since I'm just trying to present concrete results from the paper that use some concrete formulas, let's just go with this. Okay, so we will now assume that this was a purely quantum mechanical description. We will assume that it has this 2D gravity dual. Okay, so this is some dual description. But I want to emphasize that the entropies that we are computing are defined here. You always define your state and your reduced density matrix and S of rho here. And then you can try to calculate it here using some Lukowitz-Maldacena type thing. Okay, so let's just do that. So first, what we will do is we will actually need to repeat the calculation that we had done, because you see what I had picked was the region of interest was this yellow region union this guy, right? So this is our radiation region. The whole yellow region is the radiation region. So how do we draw that here? We draw that here like this, right? There's some yellow region that's going off to infinity, but it's ending somewhere before we reach the SYK, and I'm going to call this B. So this ends at B. And the time evolution model that we were going to take is to run the time forwards on both sides, right? So as time goes on, these regions will go like this. And as we had argued, this evolution by h right plus h left is not a symmetry of the theory. So the state will be time dependent, and its entropy, as we will see, will grow linearly in time. Okay, so now we want to calculate the entropy of this thing for initial time. And let's also remember, I had given you the answer last time, that the entropy as a function of time will look like a linear curve, and then it will saturate. So it will saturate a time of order, it will saturate at a time of order S black hole. S as a function of time, S rad as a function of time. Okay, so we are now going to calculate this part. Okay, so we draw again this big Minkowski diamond, such that we have these things embedded like this. So this is supposed to be the ADS2 region. These are the flat space regions, and we have our point here and here, right? So this is the t equal to 0 slice, and we have evolved it forward. So I called it P and Q now. So this is the point P, and this is the point Q. And from this point of view, the entropy we want to calculate, maybe I can just draw this slice, was the entropy of this union this, but by the purity of the state, it's also the entropy of this region here, right? Of this region here. For what? Mixed global state? Well, we already purified the state, right? That was the point, by introducing a second copy and so on. Okay, so this calculation will not have any gravity or anything. In fact, I could have presented it earlier when I was doing that thermal entropy. So the name of the game is just to write the coordinates of P and Q and just use the old formula. So there's some t comma y coordinate. So this is t comma b, right? So we are moving that point P on this hyperbolic trajectory. We are increasing the Schwarzschild time t or the Rindler time t, keeping b fixed. And q I will not write because q is on the other side. So the t comma y coordinates were only defined here. Okay. So, but I will write them later. So we have y plus y minus. It is t plus b, t minus b, and x plus x minus coordinate is e to the t, e to the b. We have to exponentiate this. And we have to put a minus sign and exponentiate this with a minus sign. So e to the minus t, e to the b. Okay. And the point q coordinates we can just write by looking at this, because the point q is the reflection of p in the vertical line. And the vertical line is x plus equal to x minus. And whenever we do such a reflection, we just end up interchanging the coordinates. So the coordinates here are going to be minus e to the minus t, e to the b, e to the t, e to the b. Okay, so those are the x plus x minus coordinates of q. Okay, so now we come out with our formula. S of pq is c over 6 log of delta x plus c over 6 log of delta x minus c over 6 log of omega p minus c over 6 log of omega at q, and this is equal to c over 6 times 2. I'm just going to write it. The first two terms are equal. E to the b times 2 cos t, right? Because when you take the difference here, you get e to the b common, and there's a 2 cos t, and then minus 2 times c over 6 log of e to the b. So this factor is the same that we calculated before. That was the square root of x plus x minus. So when you multiply x plus x minus, you just get e to the b. So that's the thing. Okay, so what is this equal to? This is equal to c over 3 log of 2 cos t, if I got it right. Okay, and so again, there is some t over beta and so on. But like when t is much, much bigger than beta, this is linear in time. Okay, so this calculation is like a demonstration of the linear increase of entanglement entropy purely in Minkowski space. Like if you had taken CFT2 on Minkowski space and had started moving these regions up in time, it's like the simplest model of time evolution, you get an entropy which is growing linearly in time, and that basically just produces that first curve. So this is like, the fact that the state is time dependent. And generically it just goes linearly in time, but you have a more precise formula here. Okay, so far this island stuff has not made an appearance, and now it will, that's like the next thing to do. Yeah. Okay, so now things are a bit hard. It's a little bit tough to calculate the exact entanglement wedge of, because we are in a total pure state. Instead of calculating the quantum extremal surfaces for this region, we can alternatively calculate the quantum extremal surfaces of the complement region. But the complement region is like a union of two intervals, right? If we look at that picture, it's like some interval here and it's a union of two intervals. It's not easy. What we noticed was that it's enough to treat the two intervals sort of separately at late enough times that there is not much mutual information between them, because initially these were entangled, but because this system is mostly coupled with this, by the end of the time evolution, which means time's much, much greater than beta, this is mostly entangled with this. So it's enough to just compute the entropy of the following region and then double it. This is an approximation, and it's good approximation at late times. This is just some trick. So we have this. So what we are going to do is to calculate the entanglement wedge corresponding to just one region, so 0B. So this is now the region of interest, and we want to calculate the entanglement wedge for that. Okay, so I forgot to write what the dilaton becomes in this coordinate. It's going to be important. So phi was like a cosh rho basically times some coefficient, but that's a cot hyperbolic of y. So that we should just note from here. Okay, so we have this region on the this region B. This starts at B, and we say that there is a candidate extremal surface at minus A. So candidate QES at minus A. So the interval minus A to B is the entanglement wedge of that blue region. Okay, and because it's an entropy of one-sided region, under this time evolution it doesn't change, right? It's a constant thing, as Ashok was asked last time. Okay, so then we just do the calculation. There's nothing hard now about it. So S gen of A, right? It's a function of A, and we are supposed to extremize this, is 1 over 4G. So G, since it was dimensionless, I will set it to 1/4. So it is phi r 2 pi phi r over beta. That is this A, right? A was equal to that value times this cot. So we have cos 2 pi A over beta. Okay, now I also restored beta here. Beta was 2 pi. Yeah. Plus C over 3 log of beta over pi sinh of beta pi over beta p plus A. What is this? This is just the thermal entropy of a CFT in an interval of length A plus B, right? This is the first calculation we did today. It has this C over 3 log and sinh and so on, right? But now we have to remember that this point minus A is in ADS2 space. So the ADS2 Weil factor is this Weil factor. So we have to put an extra contribution from the point negative A, which comes from here. So it's negative C over 6 log of beta over 2 pi sinh of 2 pi A over beta. Okay, it's basically sinh of the spatial coordinate up to some 2 pi's and stuff, right? So this is the CFT2 thermal entropy, and this is from minus C over 6 log of omega at negative A. And remind you that this is supposed to be area over 4G plus S bulk matter. The bulk matter is a CFT2 which is flying around on this space. Okay, so now we just go and minimize this, right? So we need to just set ds gen by dA equal to 0. And now it's just some trigonometric functions. We can do this. The condition becomes 2 pi phi r over beta, 1 over sinh of 2 pi a over beta equals C over 6 sinh pi over beta a minus b over sinh pi over beta a plus b. So let me call it a star. Okay. So this is the equation that determines a star. It's not easy to solve exactly, but it's what it's like, gives you some answer. Okay, I want to explain one limit of this, even though we can't solve this exactly. It's good to see what it looks like. The solution to this looks like. So we can take the limit. Yeah. This was in the thermal state. Vacuum didn't have this sinh, right? So we used an initial omega trick to calculate the thermal entropy of a CFT2, right? Here, like the CFT in this region is in a thermal state, right? So that's what we are using. See, the CFT on this diamond is in a thermal state. It's being purified by this. So you could work in some global coordinate on this bigger wedge. I'm just choosing to work with the y coordinates that are, just valid on this. So then I should use the thermal entropy formulas that I had before. But there is this one extra contribution from that omega that I just did. Okay, so we can take a limit which is phi r over phi r times temperature is much, much bigger than C. So what is this? This is a slow evaporation limit, because phi RT was the entropy of the black hole above extremality. And C is like how many fields can the black hole evaporate into. So this is like saying you have initially a black hole which is very big, and every unit of time it will emit C units of entropy. So if C is much smaller than the initial entropy, this will have a slowly decaying profile. And in that limit, you can approximate, you can check that approximate all cinches in this by exponentials. That just comes out of the analysis. So you find A star is B plus some beta over 2 pi log of phi r over beta C times some factor, some 24 pi or something. Okay. So it's just B plus some amount. But the point is that it is somewhere here, right? It is not at y equals minus infinity. So the picture that we should now draw is the following, that we have some ADS2 black hole. We coupled it to a bath at the same temperature as the black hole. And we started evolving this system forwards in time. So we started moving these Cauchy slices upwards and upwards. And we took this to be our radiation region. And we found that there is an quantum extremal surface here, and by the argument I was just giving, some quantum extremal surface here. So the full yellow region is now the entanglement wedge of the radiation. Because this minus A that we calculated, this minus A to B was the entanglement wedge of this little complement region. And similarly for this guy, so the total, the radiation region is dual to this. So this is the entanglement wedge of the yellow region. So you see it's disconnected, it contains a disconnected piece, and that is the island. And one thing, the last thing we should do is we still need to get that flat part, the top thing. You just take this value of A and you plug it back in here, okay, to find what the S gen of A star is. And you will find that it is essentially given by the first term. Oh, sorry, I drew it wrong. You're right, thank you. It should be here. Thanks. Yeah. The point is we didn't find the location of the island. We found the location of a quantum extremal surface, A star. So quantum extremal surface is supposed to be the boundaries of the island, right? So here we calculated the entanglement wedge of this region, which here would be represented by this little interval that I have left out. Okay, so the calculating this extremal surface was a trick using this purity to actually find the entanglement wedge for the radiation. Okay, so then you're done. So this is like a quantum extremal surface at late times for this radiation, which gives a entropy which is almost constant in time. It is constant. It just is given by this first term. Actually, did I write that? Yeah.
Yeah, so A star depends on B, right?
Yes.
So where do you choose B?
So B can be taken to be epsilon. So B was just introduced as an additional parameter.
Yeah.
Because you see the SYK is just at 0. So you can just take B equals some small epsilon and then define. So this is just like, where do you want to say the black hole ends and the radiation starts?
Okay.
So the B is not so important. So B you can think of as like 0.
Okay. So it's to start from beta over 2 pi something.
Yeah.
And it resides always in the black hole, as Gopal said.
Sorry, say that again.
That minus A, the point,
Yes.
should always lie inside this wedge.
Yeah, it was outside the black hole horizon. So here,
Yeah.
so it is outside the horizon, like it was corrected. Yeah.
Okay, for all beta and for all phi.
Yeah. Okay. In fact, you can see that this term does not contribute much to the entropy because, as I said, A is getting very big. So phi r over beta c is very big because of this condition. So A star is kind of deep inside, right? A star is a big number basically because this argument of the log is very big. So you approximate these cinches by exponentials. Log of A here you get, and here you get log of 2A. Log of cinch will cancel. So here you'll get something linear in A, here you will get 2A, but here the coefficient is half. So these two terms almost cancel. And the flat line, that thing at the end, is just calculated by this term. And this coth is almost 1, right? Because A is big. So then the value of S gen at the extremal surface is just this thing, which was the black hole entropy, right? This part was just the black hole entropy. So you see here this interesting fact that even though to get the extremum value in setting the derivative equal to 0, these matter terms were important because they have some log, right? So the log, the derivative can be singular. But when you actually go back and plug the value of the extremum back into the function, the matter entropy is not actually contributing that much to the final answer in this case. So there is this interesting interplay between this S matter and bulk term. Well, see, this is some function of S gen of A. There are some logs here. Log of x has a derivative which is 1 over x, right, which can be very big. So here, in solving this equal to 0, of course, we are balancing this term, which is area over 4g, with some stuff coming from matter, right? But we found this extremum where A is very big. And on the extremum, it is not mattering very much. It's like when you do the Stirling approximation for the gamma function, you have these two terms. To set the derivative equal to 0 to find the saddle point, both terms are important. But the x log x term, which is the dominating term, comes only from one of the terms in the saddle point. Right? There's x log x minus x, but the x log x is much more important than x. So it's like that. Yes, yes. Okay, so this sort of finishes the technical part of the things I wanted to present. This was this calculation in this paper with Almeri and Juan, and we realized this transition from this linear to the flat line. Okay, so now just let me present one scenario of black hole evaporation where how I think about the issues raised by Suvrat et al. I have not thought about these much for the last 3-4 years, but let me just say these comments anyway. Okay, so let's consider the following. So now it's the math part of it is over, and these are just some speculative comments at the end. So imagine an ADS, no bath, no nothing. We just have ADS4, not even ADS3, some ADS4 or ADS5. You take some matter and you collapse it to form a black hole. Okay, you form a black hole, and let's say it's a small black hole. By small, I mean its radius is comparable to LADS, but its specific heat is negative, right? We have those kinds of black holes. So this black hole will evaporate, like it will emit some particles. So we have some matter, forms a small black hole in ADS, and it evaporates. Okay, so it's like kind of spherically symmetric. We had a spherically symmetric shell of matter on the boundary. It was in a pure state. Its entropy was 0. It fell in, formed a black hole, and out came the radiation, right? No one will doubt that if you took the entropy of the full boundary region, of the full boundary, at any time t, it will continue to be 0, right? You have a pure state. The boundary person doesn't care whether a black hole is forming, whatever is happening is just a unitary evolution. It would stay 0, right? So this is like saying, if you believe in ADS-CFT, all the information is always at the boundary, and this just stays 0. But still, there is an interesting question about, can you, at some intermediate time before the black hole has fully evaporated, give a definition of the black hole and radiation degrees of freedom? Yes, from the bulk semi-classical point of view, we have this intuition that there is some black hole region for up to R equals 100 M, and then there is some radiation. But on the boundary, those distinctions are not so clear, partly because we are in this spherically symmetric setup, and radiation is being emitted in all directions equally. So, there is not a spatial subregion of the boundary to which we could apply root Takayanagi and also say that that is the radiation region. Somehow the radiation and the black hole parts are mixed up everywhere on the boundary, right? So you cannot separate them. Okay, so this is just one comment. So here we kind of failed to identify these subsystems, but no one would, debate with this thing. Okay, now let me just say a speculative thing.
So Raghu, can I add one thing to this, since you mentioned very kindly this example? This is actually a great example.
Yeah.
We can ask a question to which I don't know the answer, which is, of course, the full fine-grained entropy is always 0.
Yes.
Let's say we start with a very coarse-grained entropy, where we are just measuring a few operators.
Yeah.
Then that guy probably still obeys the Hawking curve.
Yes.
And then we start, slowly making it more and more fine-grained.
Yes.
At the level where we reach e to the minus s, where we are measuring correlators of e to the minus s,
yeah.
then in fact, it's possible that in the intermediate region, before the black hole has evaporated, we are able to see that things are still pure. But the black hole, the state on the boundary continues to thermalize because the entropy of the final Hawking radiation is larger. So it might even
coarse grain entropy.
Yeah, so I'm coarse-graining, but I'm coarse-graining at e to the minus s, where s is the entropy of the black hole. I mean, so I'm fine-grained, not to infinity,
Okay.
but I'm measuring effects of size e to the minus s.
Okay.
Then it might be that at that level, it's possible to reconstruct the pure state from the middle region, which you have drawn, but not from the final region, because the final region has even larger entropy, which is e to the minus s prime, where s prime is the entropy of the Hawking radiation. So it might in fact be that, it's easier to extract the information before the black hole has evaporated than after it is evaporated, just by the second law of thermodynamics on the boundary.
But that I agree, yeah.
Okay.
Yes, I mean, the state gets more and more complicated as time goes on, so to reconstruct it, it's harder at late times. Okay. But still, like, there is still a question, like, if I'm a bulk observer, I would like to know, is there a subalgebra on the boundary, which I call the black hole observables, and is there a subset or subalgebra, I don't know, that I can call the radiation region? And that is, I think, really the question. So here is some speculative thing, which I don't know who it goes back to, but I've heard it in, yes.
Can I confirm something?
Yeah.
So if I'm
Who is speaking? Oh, yeah.
if I'm just sitting with a radiation collector or something and looking at the black hole,
Yeah.
the switching of gravity complaint we raise, is it about like, and I'm trying to predict what the
Sorry, say your thing again. Which setup are you in?
I have a radiation collector or something, and
Radiation coupled to something?
radiation collecting some device.
Some device collecting
Yeah.
radiation. Okay.
And then I'm trying to predict what this device reads.
Okay.
Is this complaint about switching of gravity asymptotically about I should also include the self-gravitational interaction of the apparatus, or is it that I have to include the gravitational interaction
No,
between
it's just
the
that if you
apparatus and the spacetime?
right, the complaint would be that your device may not exist in all branches of the quantum gravity wave function, because your space-time, even though there's weak gravity, there is still fluctuating. That your space-time might just not be what you thought, and you might not have a device at all. Right, that's the kind of nature of objections that come.
No, this S of t equal to 0 assumes there's some measurement I can do, right? Like,
Yeah, so I was hoping that you are asking if you don't switch off gravity, what happens? No.
there are two things you switch off, right? The gravitational self-interaction of the apparatus and the gravitational interaction of the apparatus with the spacetime. Which is the worst thing, or are both of them problematic? Like, because when you switch off,
I don't know how you distinguish those two. What does that mean? I mean, this G Newton is controlling both of them, right?
no, there is radiation exchange between the apparatus and the, let's say, horizon, and the radiation, the self-interaction of the apparatus. Because when you switch off gravity outside the black hole region, you're kind of switching off both, right? There's no gravitational interaction within the region, and also
How do you switch off one and not the other?
I don't know. I mean, there seems to be some complaint raised. I'm just trying to clarify, like.
Yeah, right now I don't have any comments about it.
I want to just say it's not an issue of a complaint. I don't want to phrase it in terms of a complaint raised. I think the issue more is what is the essential physics we are learning from black hole information. Even here, like what Mathur and so on ask is, how did information from the interior get into the radiation region? And I would feel personally that the essential physics we are learning is that the reason information leaks out of the black hole is because gravity localizes information unusually. No-hair theorem is not valid. So now the page curve was derived by making the incorrect assumption that gravity is like a local quantum field theory. Now, if we ask the right question, we can make that intuition come correct. But the complaint is not that there's something wrong with the calculation. It's just that, the real physics, I feel, is that gravity is localizing information unusually, and we should not try to somehow wish that away. We can if we want,
Yeah,
if you ask the right question, but yeah.
I asked a physical situation, right? I asked, like, I want to predict what the dictator sees. Would you tell me I have to be careful about how the dictator interacts with itself to correctly predict what it sees, or like?
I think Sandip had and Spenta had a question. Yeah.
Thank you. No, I just wanted to ask the following. It's not very precise. The original ADS-CFT was derived by first starting with a full D-brane solution, which is asymptotic to flat space, right? And then sort of zooming in a precise way. But now let's restore the asymptotic region, which I think is in the spirit of the calculation you presented. Is it then possible in some reasonably precise way to say, this is the information in the n equals 4 theory as opposed to what is outside? When the n equals 4 theory, also described as ADS,
This or
yeah. So I'm saying take your setup, but now add the asymptotically flat
yeah,
region.
yeah.
Now, is it possible to say that, you have some radiation which is streamed out
Yeah.
and reached far away?
So you want to form a 10D black hole by collapse
That's
in
right.
10D,
That's right.
and which is sort of near extremal and
That's right.
Right,
That's
right.
right. But now we have that asymptotic region.
Yeah.
Can we make reasonably precise the fact that there's entropy or entanglement between the n equals 4 and the radiation, or
Yeah,
some
again,
part in the n equals 4?
I think there are differences between strict decoupling and almost decoupling. Like the nature of this localization of information at infinity is a little bit discontinuous, right? Because as long as you have G Newton equals epsilon, somehow the way the information gets is changed. So I think taking the decoupling limit and having the flat space region attached, for some questions, that kind of a thing can be discontinuously changing. So I think if you have the 10D flat space, then I could naively say that if you assume in all these flat space arguments, which I haven't carefully scrutinized, that all the information is near like the Scri plus of the 10D flat space, and that you shouldn't be able to sort of restrict to some n equal to 4 near horizon subregion. But in some sense, your comment is sort of helpful in that sense that the decoupling limit is telling us that there is a throat region in these near extremal black holes which kind of becomes self-independent, right? Because that is how you derived ADS-CFT in the first place. So there are some throat degrees of freedom which are the n equal to 4 super-Yang-Mills degrees of freedom. So I don't know.
But I just want to say, if we had succeeded in making this, first of all, so you want the black hole to evaporate. So you don't want it to be completely extremal. If it's extremal, it won't evaporate. So you want, so that's a little, so then you won't have this exact throat. And if in a setup where the black hole is evaporating, you did succeed in making it completely independent, then you would come back to the Hawking paradox. I mean, the kinds of objections I'm saying, they're very physical to resolving the paradox, because the question is, how did the information enter the radiation? It looks like the information was in the infalling matter. And the answer is that, in fact, the horizon is not information free. If you measure correlators to good enough accuracy at the horizon, they know what went in. And that follows from the constraints of gravity. So if we really succeeded in getting locality in gravity in some way, then we would be in trouble. We would lose the paradox. And the island proposal is also saying that. You see, the radiation region is far away. It in fact knows about the island which is inside.
But I think these words are kind of a bit dangerous to just say at the level of words, because in the PSSY, sorry, Spenta has a comment. Sorry.
Shall I ask you?
Okay, maybe, is it related to what Suvrat was asking? Or
No, it's related to something you said before, but perhaps you complete this discussion.
Okay, yeah. So the thing I wanted to say is, in this PSSY model, there is one boundary path integral that you set up, which calculates the entropy as a function of time. Okay, that's one calculation. You get some number as a function of time, you can draw it. There's a second calculation, which is applying this PETS map operator. You set up a separate boundary path integral for it. You're not trying to do everything all at once. You try to apply a PETS map operator to the radiation, and in that calculation, there is a new wormhole that appears, and the information clearly gets there through that wormhole that is being used in the PETS map derivation. So we should not try to use one semi-classical geometry to answer all questions. See, this island just came out of doing the replica wormhole calculation. It is not some fundamental primary thing that I should attach some meaning to in my geometry. Because the fundamental thing is calculating trace rho to the n on the boundary. And then whatever bulk saddle point you're getting. So that's why I don't want to interpret any of these calculations or the existence of the island as telling us something about how the information got out. If you want to probe that, you ask a different question, which you set up differently on the boundary. There are different saddle points that contribute, and you get a different answer. And this PETS map is a very good example, I think, of exhibiting that kind of thing. So, yeah, Spenta.
Yeah, so you said that, when we, in the bulk actually, one can envisage the formation of a black hole, collapsing matter.
Yeah.
So suppose I'm on the boundary actually, and I'm
Yes.
a boundary theorist or an experimentalist. And what am I observing? I'm observing very high energy particles being collided
Right.
and forming some sort of a thermal state which then evaporates.
Right.
So in a gauge theory, this would be formation of the deconfinement, localized
Yeah,
deconfinement phase, and then,
confining in.
confining in, and the glue balls are.
Right. Exactly, yeah.
So now the question was the following. See, so you raised the question of how to describe in terms of this operator language of
Yes.
algebraic
Right.
theory. So I think the deconfinement phase may not be that difficult because we understand local.
You're saying like maybe in the intermediate time, some degrees of freedom are deconfined and some are confined.
Yes.
The deconfined part is somehow the black hole part, and the
Yes.
confined part is the
That's right.
is the radiation that has
Yes. And
roughly,
so the pointed question is, how do you describe operatorially, or in the language of algebraic quantum field theory, the deconfined phase of a gauge theory?
Well, in particular, when you have both deconfined quarks and mesons present together, in some sense, right? Because
yeah, I mean, I'm just thinking in terms of pure gauge theory. So you just have glue balls.
Glue balls, yeah. So you have deconfined gluons versus glue balls. You have some fraction of both of them.
That's right. How do you describe algebra?
How do you distinguish them?
Yeah, there was this paper a long time ago by Shiraz and company. I mean, about these plasma balls, in which they identified a blob of deconfined phase on the boundary of ADS, essentially corresponding to black hole, and in fact they were able to map the horizon to the phase boundary. So I have that model in mind.
Okay, yeah, maybe we should discuss this. I have not studied that paper, but since the time is over, but I did want to present one scenario which I have got from discussions with Arvin, who was my office mate at Stanford, but I think maybe there was some discussion with people at Berkeley. So here is the alternative thing, where you could plausibly imagine radiation to be, localized in a spatial region. So imagine that you have this setup where there's a black hole that forms. Okay, so there's some black hole that forms, but somehow the black hole is moving in one direction. So the black hole sort of has a velocity, it's moving towards this point on the boundary. So it's moving in time, but it's kind of approaching it. So if you then believe that the Hawking radiation would also be emitted in some kind of preferred angular directions, which are set by the velocity of the hole, you could imagine that most of the radiation at late times ends up in some spatial subregion. So because the black hole is moving as it is evaporating, okay, so now, this is very hard to do. This is just at the level of words. So I don't want to really back this up. If people really push me, I might just, But, here now there's a candidate where there's a lot of Hawking radiation which has ended up here. And then you have a hope of maybe having some kind of island that I was drawing in the first lecture or the second lecture, where you just have, so now what you have achieved by this motion is that the Hawking radiation is now in a spatially limited region instead of being everywhere like here. So this would be like a spatially inhomogeneous plasma on the boundary, where there's some confined stuff here and deconfined stuff there or something like that. I don't know, these are just some words, but at least as I think we were agreeing to this setup, there is no sharp objection of having these disconnected pieces of the entanglement wedge. So I'll stop there, and thanks for listening. You've been a very good audience. Thank you.
Any further questions?
Just something that confused me, Raghu, that this Marolf-Maxfield scenario, where there is no mass to the graviton, no bath, anything. Okay, it's a scenario because you can't do calculation of
which they have many papers.
Oh, this is the flat. In the flat case, they compute the swap entropy at scribe plus, and
they have some of these permutations and so on.
Exactly. Okay. So, is there something problematic with the proposal, or is it just because there is no computation, people don't take it seriously?
Yeah, to be honest, like that paper, I haven't really tried to really. There was this old paper of Polchinski and Strominger.
Yeah, it was based
which
on
basically said that if you collide many black holes, there can be wormholes between them, and that can allow you to get some statistics. So that's a bit like saying, I compute some higher point moments.
Yeah.
And those can be, at least the statistics of those coarse grained over, I don't know, something. Like in JT gravity, you coarse grain over this random Hamiltonian. Those can be captured. But I don't believe those kind of arguments can really give you the fine-grained, like von Neumann entropy, really the details of it in some actual microstate. Because this page curve is also some approximate, right? Like if I take an actual system and let it evolve, there will be some profile to this. It will not just be a tent. So the challenge is not to compute these straight lines. It's in a given microstate. You have to compute the actual curve, and I don't think any of these wormhole-based things can really calculate the precise, really with all the details. A more smoking gun example of this is this noise on the ramp. If you've seen these plots, the people have the spectral form factor, it dips, there is a ramp and there's a plateau. This is some average curve in some disorder average theory. The real thing, if I have n equal to 4 super Yang Mills, will have this noise, right? So if you really believe that the gravity is dual to this curve, the gravity should be able to calculate this. But the wormhole that you have only calculates this part, not this stuff. So we don't know all these things, I think.
So I had a comment about what you said earlier. I actually agree with you that it might be that some of these things maybe can be understood in this way of looking at some other semi-classical geometry. In fact, the simplest case to examine this might be empty ADS, where already we can measure things at the boundary and we can pull out information from the middle. So maybe there's a way of understanding that by saying when you actually do the experiment, something happens. And
there's
somehow,
some wormhole.
Yeah, maybe. On the other hand, the basic physics of this is pretty simple and you can frame it entirely at the boundary, right? It's just that you throw in information at from scry minus, as Alok was describing, and that information kind of just doesn't go in, it leaves the tail, and you can just show it leaves the tail at infinity. Now, if you want to relate that to the bulk geometry, you might need to say things about wormholes and so on.
Yes,
but the basic physics is all in the weakly coupled region far away, you can kind of make that comment.
Yeah, but I think there is value, just like, let's say I just wanted to calculate the entropy of some system. Like the cigar has some value, right? Like the cigar is not just some asymptotic geometry, there's some area of the horizon. So similarly, these double cones, these wormholes, yeah.
To see this concretely in some of these, even in empty ADS, in fact, to somehow argue that when you do this experiment, something else happens.
Yeah, you do something complicated at the boundary of empty ADS, and it kind of can make a wormhole to the center of ADS.
It would be nice if if that could be done.
About this hyperbolic,
So am I allowed to take beta going to infinity limit?
Beta going to infinity, that's the zero temperature limit. Then it doesn't evaporate, right? Then let's see, what would be the contradiction? So when beta goes to infinity, T goes to 0. I guess you won't satisfy this condition first of all. Yeah, I don't know, I don't remember what the details, what happens. Here I'm imagining you're sort of hot enough that you at least have this limit and you can do this approximation.
Actually, I am curious to know, is the issue of massive gravity also arise in the de Sitter space? Because I saw a paper by Hao Yasunori, so where they computed the page curve in de Sitter space using DS correspondence. And they found, they are claiming that they get the page curve from massless gravity.
Oh, I was looking there, so maybe we can, sorry, I don't have anything useful to say.
Okay, last question.
Sandip,
Sorry, I want to ask this question for further, so you can all gang up and beat me up at tea time. Okay, but my question is to Suvrat and you and all that. There is a sense, it might be a little imprecise, but there is a sense in which I'm sitting in this room and not somewhere out at Scry plus, I plus, or whatever, right? And maybe you can recover that information by going to spatial infinity. But I think, Suvrat, you'll agree you have to do some incredibly complicated experiment or operation. You may not agree. But my only point is, in that colloquial sense, can't we ask in the course of black hole evaporation, where is the information? And ask, how is it, coming?
Yeah, and my sort of,
and so on. That's what I want to ask. You can all tell me later.
Yeah, I want to say that if you kind of be a bit naive, like this naive split between 100m to infinity and 100m to inside, I think that should work. Maybe you just need to relax some constraint, like, we are getting all this information at infinity by imposing all the constraints and working with all these things. Maybe if you didn't impose those constraints, maybe if you were a bit naive and just forgot about some of them, you would get some approximate description, but it would roughly look like that the information is separated, from inside 100m and outside 100m. Now, I don't know how to make that precise, but
different answer. In fact, Alok discussed this in the morning. He said to all orders in perturbation theory, you can define operators that look perfectly local. When you're in an excited state where the energy is much above the Planck scale, the energy of this room is much, much more than the Planck scale. So you can define, in fact, an amoeba is more than a Planck scale. So if you have an amoeba as a background, you can define operators that are local to all orders in perturbation theory. That's the sense in which we see everyday locality. But in that, if you only work at that order where you work in perturbation theory, there is also an information paradox. The state never gets pure. Because to see the state becoming pure, you have to keep track of corrections of size e to the minus s. When you keep corrections of size e to the minus s, then you also see this fact that, information is holographic. So, this is kind of the key issue. So you shouldn't try to get both worlds at the same time, where you also get locality and you also see, the fact that the state is pure. And in some examples, like these examples of a non-gravitational bath, you can do both. But it seems to me that the physics essentially is that because information is holographically stored, that's why, you don't lose information. So yeah, that would be my answer.
Let's end the session and thank Raghu again.